What if you could search through 500 documents and get a precise, cited answer in under 3 seconds? Not keyword matches. Not 2000 results found. An actual answer with the exact paragraph and page number. That's what a RAG pipeline does. And today, I'll show you exactly how to build one. Retrieval-augmented generation is the architecture pattern behind every serious AI application right now. ChatGPT with file uploads, Notion AI, legal document search, customer support bots. They all use RAG under the hood. Companies that skip this step pay the price. Microsoft's Bing Chat hallucinated fake legal cases in 2023. Google's Bard cited articles that didn't exist. The problem wasn't the LLM. It was the lack of grounded retrieval. Without RAG, your AI is just guessing. With RAG, it's citing sources. This concrete. You're a legal tech company. A client hands you 500 PDF contracts and asks, what are the termination clauses across all vendor agreements? Here's what most teams try first. Approach 1, manual search. Someone opens each PDF, hits Ctrl+F and types termination. Across 500 documents and 10,000 pages, this takes days. And you'll still miss clauses that say end of agreement or contract expiry instead of termination. Approach 2. Keyword search with Elasticsearch. Better. It indexes all 500 PDFs and returns results in milliseconds. But termination appears in 2000 paragraphs across those documents. Most results are irrelevant. You're drowning in matches with no way to rank by meaning. Approach 3. Just throw everything at the LLM. Paste all 500 documents into GPT-4's context window. Except you can't. That's 10,000 pages, roughly 5 million tokens. No model can handle that. All three approaches fail. You need something that understands meaning, not just words. How RAG solves this? Step by step with our 500 PDFs. Step 1. Ingestion. The document loader reads all 500 PDFs. It extracts text, handles tables, OCRs, scanned pages. 500 documents, 10,000 pages, all converted to raw text. Step 2. Chunking. The chunking strategy splits those 10,000 pages into roughly 40,000 chunks of 512 tokens each. Why 512? Too large and irrelevant context sneaks in. Too small and you lose meaning. Step 3. Embedding. The embedding model converts each chunk into a vector, a list of numbers that captures semantic meaning. Termination clause and end of agreement produce similar vectors, even though they share 0 keywords. At 10 to 50 milliseconds per embedding, batch processing handles all 40,000 chunks in under 30 minutes. Step 4. Storage. All 40,000 vectors go into a vector database, Pinecone, VV8, or Chroma, optimized for similarity search across high-dimensional vectors. Step 5. Query time. A user asks, what are the termination clauses? The query gets embedded. Similarity search finds the top 5 most relevant chunks in 5 to 20 milliseconds. Those chunks get injected into the LLM prompt. The LLM generates a grounded answer citing specific contracts by name and page. Accurate answer from 500 documents in under 3 seconds. Stock trade-offs. Why not use a different embedding model? OpenAI. ADA is fast and cheap, but for specialized domains like medical records or patent filings, domain-specific models produce better embeddings. How do you choose chunk size? 512 tokens isn't universal. For dense legal contracts, 256 gives better precision. For research papers, Dender 24 preserves more context. What about scaling? 500 PDFs means 40,000 vectors. But what about 5,000 PDFs? 400,000 vectors. Pinecone handles billions but costs money. PG Vector is free, but slows past 1 million vectors. I've seen this trade-off in production. We built a real-time dashboard for school districts across the US. Initially, every load hit the database directly, no caching layer. When hundreds of schools loaded dashboards simultaneously, queries choked. We introduced Redis, and the difference was night and day. A caching layer isn't optional at scale. The same applies to RAG. Cache your embeddings, cache your retrieval results. Things that make or break a RAG pipeline. First, chunk size matters more than model choice. Get your chunking strategy right before optimizing anything else. Second, vector search is not keyword search. Embeddings capture meaning, which is why RAG finds end of agreement when you search for termination clause. Third, cache everything you can. At scale, recomputing embeddings is the bottleneck, not your vector database. In the next video, we'll build this entire pipeline from scratch with Python, LangChain, and Pinecone. Live coding, no slides. Subscribe to Neural Scale so you don't miss it.